All right, so next up, we're going to talk mainly about what are called z-scores. And kind of in connection to that, we're going to talk first about what makes a data value unusual or usual. All right, and there's going to be a couple of different interpretations of what's unusual as we go through this course. Outliers are unusual data values, but they're very specific. We're going to have a very specific rule for calculating outliers. Unusual is a more general term, and we're going to define that generally, as points that are more than 2 standard deviations from the mean. So if we take the mean and we subtract 2 standard deviations from it, or we add 2 standard deviations from it, anything outside of that, so if I put the mean here, and we've got the mean plus a 2 standard deviations, and we've got the mean minus 2 standard deviations. Those points, so anything outside of this range, outside of that range is going to be unusual. Unusual out here, unusual out there, okay? And a lot of times we're going to, if we're talking generalities, not a specific data set, our means, we're going to be talking about parameters. So our mean will be using that mu, and mean plus 2 sigma, 2 standard deviations for the high side, and mean mu minus 2 sigma standard deviation for the low side. Okay, so this brings us into an idea called a z-score. We're going to be using z-scores and a close cousin to them, t-scores, for the entire rest of the semester, except for a tiny little bit in not so much in chapter 3 and 4 and 5, but 6, 7, 8, 9, and 10, you're going to see z-scores. You're going to get tired of them. You will learn them. Okay, so we can think of the standard deviation like a ruler to compare different items. I like to think of the z-score formula in words. It is the data value minus the mean over the standard deviation. Because by the time this course is over, you're going to have about 6 different similar formulas for z-scores. And you can see we've already got 2 here. This one is if we have a data value and we're comparing it to the mean and standard deviation of a sample, right? And this one with the mu and the sigma is for if we're talking about a population. So this one will be for population, and this one will be for a sample. All right, they're really the same formula though, right? You've got your data value, which is your x. Some books will call it y. You've got your mean, mu or x bar, and you've got your standard deviation, sigma or s. Okay, so what this allows us to do is compare data values even if they're from different sets. So like apples and oranges, or if you're recently out of high school, maybe your SAT versus ACT scores, right? So we also can rearrange the formula to find a value that's a certain number of standard deviations away from the mean. So we can take that z equals x minus mu over sigma. We can solve this for x by multiplying through by sigma, and then adding mu to both sides. So x is going to equal z sigma plus mu. So that's a good one to know also. All right, now you'll notice that those 2 z-score formulas are on the formula sheet that you will be able to use for the exams. Okay, so can we compare apples and oranges? Why, yes, we can, so long as we're comparing a particular apple to all the rest of the apples and a particular orange to all the rest of the oranges, and then using that. So we need standard deviations for that. So for an example, let's say we have an apple and an orange and they both weigh 12 ounces, and we want to know which one is bigger. And what we really mean there is which one is bigger for its type of fruit, right? Which one is comparatively bigger? And so, of course, I haven't given you enough information. You can't figure it out. So we need to have some information. So, but if I tell you the apple is 2 standard deviations above the mean apple weight, and the orange is only 1 standard deviation above the mean weight for oranges, then right away, you know that the apple is bigger for being an apple than the orange is for being an orange. Yes, they're the same weight, but we're saying comparatively speaking, who's bigger. And you can do this we're like, because men are generally taller and way more than women on general, so you can use that to compare that. Or those of you who are parents know that you get, every time your child goes in for a well visit, they tell you their height and weight and where they are compared to all other 10-year-olds or 12-year-olds or whatever. And you don't, if you look closely at the chart, it actually does give some information on the mean and the standard deviation on that. We're going to revisit that more in chapter 6. Chapter 6 is all about z-scores and connected to that, the normal distribution. So one example here, and then you just have one, you have one in the soccer tip for chapter 8, and then a couple in your homework. So here we've got Joe. He runs the 100-meter dash in 9 seconds, which is 1.5 seconds faster than average for his school. All right, so we've got his data value, 9 seconds. We've got a mean. We've got a standard deviation. Jane, she's a pretty good jumper. She jumps 27 feet, which is 4 feet longer in the long jump than average for her school. The mean is 23, and the standard deviation is 1.6. Sorry. So the question is, who's better at their sport? Now, you're comparing running and jumping, right? This is like apples and oranges. So what we need to do, though, is say, well, who's better compared to the average for their sport? So we would calculate a z-score for Joe. We've got his data value minus mean over standard deviation. So data value is 9, mean 11.5 seconds, standard deviation 8 seconds. And if I do that on my calculator over here, there we go. All right, so we had 9 minus 11.5. Now make sure that you've done that subtraction before we divide by 0.8, okay? I see a lot of people get that mixed up. So negative 3.125. So he is just over 3 standard deviations below the mean. Now Jane, on the other hand, let's see. She jumped 27 feet for a mean of 23 and a standard deviation of, 1.6. And the trusty calculator is going to tell us, let's see, clear. So 27 minus 23, of course that's 4, divide by 1.6, we're going to get 2.5. Okay, so which one's better? Now this is a little misleading because normally better is going to be a positive z-score. So Jane here, she's 2.5 standard deviations above average. She's jumping further for her distance. Joe is 3 standard deviations below the average time, but he's running, and the faster you run, the smaller your time. So for this one, we really want to know who's further away, who has a larger number of standard deviations away from the mean. And in this case, it's going to be Joe. Because now if his z-score had been positive, that would mean he is slower than average and Jane wins, right? But he's faster than average, Jane jumps further than average, and Joe has just a little bit further away from the mean in a good direction. Okay, so that's it for z-scores. We're going to go on next to percentiles and quartiles.